Okay, well, thank you for all coming to this final lecture. Okay, so as promised, there will be a big diagram today. So, okay, but first let me remind you of what all the setup was. So there's a, okay, so, well, number field, 5 set of places, ring of S integers, and that we chose a particular a place of good reduction, and P was the prime below it. And okay, you have the usual notation for the local field, the completion, and this evaluation ring and residue field. And then here's the curve. Here's the curve whose integral points we want to find. Or, well, maybe not find, but at least prove that's finite. And last time I explained you could always reduce to the case where there's just one residue disk by just removing all but that one KV point at a time. And to do it for each of the different KV points, you can essentially have one residue disk at a time. So just for simplicity, I'll do that. So just, okay. So, and now the method of proof is to choose an auxiliary variety, a family of varieties over Y, a smooth proper family. And by the way, finite type is included in proper, so it's okay. All right, so. And also, I choose a non-negative integer I because I'm going to take ith cohomology of the fibers of this map. And okay, so then I can define the étale cohomology of the fibers. And so yeah, for each integral point of Y, I will take the fiber and then take its étale cohomology. Yeah, well, base change to an algebraically closed field as usual when you take l-adic cohomology. And you can also do this for a local point. If you have a OV point, then that defines a fiber that you can consider over KV or KV bar, and you can take its étale cohomology. And yeah, I mean, I'm using the same notation, so you might worry, oh, what if it's both? What if it's one of these that's also there? But it's at least they're compatible because you go from here to here just by restricting the group that's acting, to restricting to the gal group and restricting to the decomposition group. Okay, so I need a little bit more notation. So I hope this is not too confusing, but I'm going to use just V without a subscript to denote the de Rham cohomology of this particular fiber they've chosen. So I chose one O point on Y, and I'm going to take this. And also, maybe this is confusing. I'm going to base change the de Rham cohomology to KV. So this is, well, if you like, I think of this as a K variety, or base changes to a KV variety and then take its de Rham cohomology. So this is, yeah, so what kind of thing is this? So this is a fine dimensional KV vector space. And it has, well, because of the comparison with crystalline cohomology, it has a Frobenius operator on it, the semilinear operator, and it also has, because it's a de Rham cohomology, it has the Hodge filtration. Yeah, so it's okay. So, is there a question? No.
Just a little bit confused with the piece of notation KV.
Yes.
Yes. This is small KV. This is just a residue field.
This one is a small. This one. That's a small KV. Yeah, you can make it look smaller by making it taller. So
the completion is capital KV.
The completion is capital KV. So most of the KVs on the board are capital KVs. I think this one and that one is a capital KV. Right. Okay. Yeah. So all right. So and D, I'll just denote the dimension of this vector space. So. And by various comparisons, I mean this is the same as the dimension of any of these V sub y's for any, except that those are étale cohomology with QP coefficients. So, oops, for any y. Okay. Okay, and maybe one more piece of notation. Let me if I put SS here, that means that's the set of points that for which this representation, this global Galois representation is semi-simple. And the reason I'm defining that set is because that's the only one for which the Faltings fineness theorem will control. The theorem of Faltings we discussed 2 lectures ago. Okay, all right. So now it's time for the big diagram. So, all right. So we're going to try to bound, first of all, these points for which the representation is semi-simple. All right. So this is a subset of all the integral points, and yeah, okay. And this maps to the OV points. Maybe I'll make a little bit more. Sorry. Let me just make it a little bit more room here. Actually, let's make everything bigger. Okay. So, all right. So now, if I have one of these. Okay, let's work on the local side first. So, one thing I can do is I can take the de Rham cohomology. Yeah. So let's say, and that will give me. Well, that will give me an object, one of these filtered phi modules. Because I can use comparison with crystalline cohomology to get the Frobenius operator. Yeah, by the way, when I write one of these, this is really a category and these are sets. So when you see them both in the same diagram, you're supposed to understand that this really represents the set of isomorphism classes in the category. Okay, all right. I don't want to say more about that, but yeah. Okay, so on the other hand, you could take the étale cohomology, and so that will give you a representation of the local Galois group. And we know, because we're starting with points of good reduction here, they're integral points, that these are going to be these are going to be crystalline cohomologies. Because, the fiber above such a point is a smooth proper thing over OV, and therefore the representation will be crystalline. All right, and we know that there's a comparison between these that we talked about, I think it was last time. So there's a fully faithful functor here called d cris that takes one of these, and yeah. Okay. Now, I also have, on the other hand, I have a period map. So over here somewhere, I'll have the p-adic period map, which goes like this. And I'd like to be able to relate these other things to this. But unfortunately, there's no way. If I have an object here, which is a vector space with a filtration and a Frobenius, there's no direct way I can get to here, because this is parametrizing the flags inside V, inside this V. And unfortunately, these, if I just take a random point here, the vector space is not V. It's some other de Rham cohomology. It's a de Rham cohomology at some other point. So I need to somehow transport that. That's how the period map was defined. You transported the filtration on some other cohomology horizontally to get a filtration on that one de Rham cohomology, the one above y0. And so, but in doing this, I've sort of forgot. Here I just have the vector space with the filtration. I don't have the information about how to transport. So let me introduce, just for the sake of this diagram, just to make the diagram even bigger, let me put something in between here that remembers how to transport it. So, so let's call this KV phi. So filtered phi modules, but with something I'll call a framing, so framed. And it's going to be defined so that there is a way to go from here to here. So okay, so what is this? So let me define it over here. So define. So this is a new category. So okay, so originally the filtered phi module is just a triple consisting of a vector space, a filtration. Oh, by the way, I want to distinguish this Frobenius from the Frobenius on these other things. So I'm going to use. So I practiced making var phi so this is a var phi. Yes, it's \var. Yes, everybody knows var phi. Okay, and you can see that it's very different from this one. Yes. All right. So and then the filter. Well, I guess I could have done something with the filtration too, but okay, that's okay. I'll just leave that. But okay, so this would be a filtered phi module. But now I'm going to equip it with one piece of extra structure, which is. So this is the new ingredient, and what is? Yeah. So well, maybe I'll remind you what everything is. So this is D is a finite dimensional KV vector space. KV vector space. Phi is a semilinear operator from D to D. So it's QP linear, but not KV linear. And this is a descending filtration. So it's a sequence of subspaces, of KV subspaces of D that has nothing to do with the semilinear operator. Okay, and this new thing is going to be a KV linear isomorphism between D with its Frobenius and this sort of fixed one, this V with its Frobenius. So I mean it's a KV linear isomorphism from D to V under which the Frobenius operators correspond. Okay? So I'll think of this as being this piece. I'll think of this as being like a framing. I'm rigidifying things by labeling D by elements of D. Okay. So right. So okay. So how does this work now? Well, so now I mean the way you get this. So okay, so maybe I'll draw here what these maps are. So this is supposed to be. Imagine this is superimposed on this diagram, but these are just showing the elements, how it happens to elements under all these maps. So Y under this first map, you get the vector space is the H1, it's HI deram of the fiber of Y, and it comes with its crystalline Frobenius and with its Hodge filtration. But then I also need an isomorphism between this de Rham cohomology and the de Rham cohomology above Y0. And that's given by the Gauss-Manin connection. So that I'll put a GM here. That just means it's the isomorphism that does the horizontal transport. Oh, yeah, it's this. Okay. Okay. All right. And now, so this, okay, so, and then this map here is just, yeah, so maybe I'll just label, this map is just forget the frame, forget the framing. So just forget the iota, and then, yeah. And, okay, so now what's this map? I mean, this map is the one, well, I mean, what do you have here? You have a filtration on D, and you have a way to go. You have an isomorphism that lets you go from D to V. So you just take that filtration and transport it via iota to get a filtration on V, and that gives you an element of this. That filtration on V is a point in here. So yeah. So if you apply to this one, for example, you'll be applying this Gauss-Manin transport to the filtration here, which gives you a filtration on the, yeah. All right, well, I don't really have room here, but GM applied to the filtration on the HI theorem, XY theorem. Okay, so, all right, and then, okay, and this is just forgetting. So down here, I guess I'm not making this big enough, but so this goes down and forgets the iota, so which in this case is the Gauss. So this is just taking the filtered phi module. Oops, almost had the wrong kind of phi. All right, fill. And then going this way would be the étale cohomology. So this would be giving me the HI XY KV bar of QP. And then this, yeah, which maps here via decrease. Okay, all right. So is it? I think it's, yeah. So I think, okay. So let me just just because this is now just not just taking the drum crawl, but also remembering this isomorphism that's given by the Gauss-Manin connection. Let me label it that way. Okay. So this is all the, yeah. So this whole thing here is everything to the left here. So this is the global side of the picture, and this is the local side. All right, so now let me now complete the diagram by putting some things on the global side. So here I can also take étale cohomology, and that will give me. So again, but now I'm doing this first line. I'm taking the étale cohomology as a representation of the global Galois group, and so that will be a QP representation of GK, and well, I mean this maps to this by restricting to the decomposition group, and well this one is, and these are going to be crystalline at V, just meaning that, well, it maps into here, and now these ones here. Yeah, so this is also called, maybe also call this one HI étale, and this one too. Now here I can put, well, I'm going to put the extra conditions on what kind of representation comes from a point here. So these are going to be, by definition, they're going to be semi-simple. Semi-simple, D-dimensional. That's because that's by definition of D, and they're QP representations of the global Galois group. They are unramified outside S, and not only unramified but also and pure of weight I outside S. Yeah, so comma, and finally they're also they're also crystalline at V. Okay, so this is a subset of all the representations here. Okay, and again, all these things are really sets of isomorphism classes. So, okay, so. Right. So let me say a little bit more about these things here. So there's an action here. Let's see. There's a group that acts here. I claim that there's an action of the automorphism group of the pair V, phi. So when I write this, maybe I should say. So what do I mean by that? So aut V. When I write aut V, I mean it's like this, except isomorphism from V phi to V phi. So these are by definition. This is the set of KV linear isomorphisms from V to V that commute with that commute with that phi. Yeah, so in the Lawrence Venkatesh paper, they call it a centralizer, the centralizer of phi. I find I always the first time I heard that I was a little bit confused by that because remember phi is not KV linear. So I mean this is a subgroup of GLV, but this is the centralizer of something that's not in GLV, in GL of KV. So but you can still, I mean it's still a map, so you can still from V to V. I mean phi is, so you can still talk about it commuting with phi. So anyway, you can write it if you want to. You can use their notation, which is Z of phi. But anyway. Okay, so let me also introduce a power. I mean, if you don't like having this thing that's only semilinear, you can raise it to a power to make it linear, because phi. I mean, it is semilinear, and if you raise it to, I mean, it's acting as, I mean, it's semilinear with respect to Frobenius, and so if you raise it to the power. There's going to be some power of the Frobenius that acts trivially on KV, because KV is just an unramified extension of QP. And the Frobenius for that is just an element of that Galois group of KV over QP. So, right, so let's see. So maybe I'll define that here. Oh, yeah?
The third line is unramified and pure of what class that is?
Unramified and pure of weight I. Yeah, sorry, maybe I'm using too many abbreviations. So that's this pure of weight I. That's the condition that if you take any place outside S and you look at how the Frobenius acts on V, then the eigenvalues, well, the eigenvalues are algebraic integers, and if you take any complex embedding of those algebraic integers, they all have complex absolute value, well, residue field size Q sub W raised to the I over 2. Yeah. So, okay. So, so over here, let me also define. So capital phi will be I'll define the power of that. I'll define it to be the power of phi that makes it KV linear. So I raise it to the degree of this unramified field extension. And so yeah. So this is now. Right. So this is now KV. This is now KV linear. It's a KV linear map from D to D. Oh, well, V to V, I guess. Okay, V to V. Okay.
What's the action about V? Because this single riddle comes from Y, not Y naught.
Okay, yeah, let me tell you what, do you want to know what this action of this on here is? Yeah, so if you have so what is an object of this category? It's a 4-tuple like this. And so you just keep these three the same, and you take the iota and you compose it with the automorphism here. Okay, is that okay? Should I write this? Or maybe I'll just write it quickly. So, well, you probably remember what these things are by now. So let's. Okay, so yeah, so what were we saying? So yeah, so if you have alpha, say an ought acts on one of these objects, D, var phi, fill, and then iota, or let's say it sends this one to the same. Okay, the first things are the same. First three are the same, and then you compose these. Yeah, I think that. Yeah, I think I got it in the right order. Yeah. Okay, so yeah, so that's yeah. In fact, let me say also about this. if you take this forgetful map that forgets the framing, and you ask what are the fibers of this map? So the non-empty fibers are going to be orbits under this group. And that's just because if you have two objects here that are the same except they have different framings, then those two different iotas, those two different isomorphisms, are going to differ by some automorphism on the right-hand side. So yeah, so okay. Now there's also there's also a group that, remember what this is. This is the, maybe I should remind you. This is the set of flags in V of where the subspaces have appropriate dimensions. So, all right, maybe I should. Okay. So maybe I'm putting too much in this diagram, but all right. Well, it's equals. Okay. So there's also an action here of the group GLV. Like these are just flags of KV subspaces of this KV vector space. So if you have an automorphism of the vector space, you can just use it to move the flags around, to move all the subspaces around. So yeah, so you have that action, and this is this, and there's something in between. I mean, if something commutes with phi, it also commutes with any power of phi, and therefore this is contained in here. And this is an actual kind of centralizer because this capital phi is KV linear. So this is actually it's like an algebraic group inside GLV. It's like, or more precisely, it's the KV points of an algebraic group of this. So yeah, so you can talk about, for example, its dimension and stuff like that as an algebraic group. This one in the middle. So right, and well, maybe as the diagram maybe suggests. This action of this group here is compatible with the action of this group here, because if you think about what these are doing, well, I mean, you're if you act by something in V here, if you apply it to the output, you're just going to do the same thing over here, and also the Frobenius is. Yeah, okay. Is that okay? It's almost harder to. Yeah, all right. So, okay. So I think I'm now ready to say what do you get out of this whole diagram now? So what is the upshot? So the consequence of the diagram. So here's the claim. Well, maybe I'll just talk through it first. So we're trying to bound this set, okay? So what we're going to do is look at where the set goes under all these maps. So I mean, it goes everywhere, right? Because this is a commutative diagram, and you can just go. You can go by various paths. You can go anywhere, and so. In particular, it goes down here, and we know that this set down here is a finite set by Faltings' theorem. Because I mean, these are exactly the conditions that were in Faltings. I mean, as I said, the pure weight I ensures there are only finitely many possibilities for the traces at any given place. And I have even an extra condition that I didn't need for Faltings' theorem, this crystallina V, but that just makes it even smaller. So yeah, so this is a finite set, and therefore the image of this down here is finite, and therefore it maps to a finite set here, maps to a finite set here, and it maps to a finite set here. So there are only finitely many filtered phi modules that are going to be relevant. Now, okay, now where could this set land here? I mean, just because, yeah, so I know it has finite image down here, but does it have to have finite image here? And, well, it's not obvious because this is not a finite to one map. So all I can say is it's going to land in the fibers of this finite set, in the preimage of this finite set. But I mean, I know what these preimages look like. They're orbits. And so what I can say is that these semi-simple O points are going to land in finely many orbits here. And those finely many orbits are going to map to finely many orbits here because these compatible actions. So okay. So let me just write the conclusion, and is that this set of points, which we're trying to prove is finite, this is mapped by the period map. I mean that's one way of going to that flag variety into finely many orbits. Finely many orbits. And I could say orbits of this algebraic group. Finely many orbits inside F. Okay. Was that okay? I mean, I went through a lot of steps here, but it's all basically just walking around the diagram. So yeah, okay. So as a corollary of this, if suppose you happen to know that the dimension of this algebraic group, as a KV algebraic group, is less than the dimension of the Zariski closure of the image of the period map on the local points. So if that's true, well, I mean, then these finely many orbits, I mean, that's going to be those are going to be some algebraic varieties inside the flag variety, and if each of these is smaller dimensional than this Zariski closure, that means there's going to be some algebraic function on this, non-trivial algebraic function that vanishes on all these orbits. Because I mean, it's just fine union of lower dimensional varieties. So what you get from that is that there'll be some function, some algebraic function on this variety that vanishes on all these orbits, but does not vanish on all the OV points. So what you'll conclude is that y of O semi-simple will be contained in the zeros, in the set of zeros of some non-zero function. And well, by the time you pull it back under the period map, it's no longer an algebraic function because this is an analytic map. But it'll be some analytic function. It'll be something given by power series on each residue disk. Well, and there's only one residue disk here. So okay, in this case where I've restricted to having one residue disk, there's just going to be one non-zero analytic function on that disk. So some non-zero analytic function on this residue disk on y of OV. And therefore, well, if you have a non-zero analytic function, just a power series on a one-dimensional disk, that therefore it's going to be finite. Okay, so this is like this condition here. This dimension condition. This is sort of like, it's sort of the analog of the Chabauty condition that you need. This is the sort of dimension condition that you need in order to get this analytic function that vanishes on the integral points. All right, so okay, so that's the upshot. So I think I'm all done with the big diagram. So. Oh yeah. So this only tells you about the points that have for which the Galois group for which the Galois representation, the V sub y is semi-simple. Yeah. So you need and so it's rather painful. I mean, you have to have a separate argument to handle the non-semi-simple ones, the points in here that are not in here, and you have to prove that that's finite in some other way. And so yeah, this is a major headache, and well, yeah. So I'll show you how this works in an example, but this is one of the most difficult parts of the argument.
But you don't expect there'll be any points there.
Well, at least if this is a family, if x over y is a family of curves, then actually Faltings proved that all the representations are semi-simple. So, and I mean, but that's as I said last time, that would be cheating, because what goes into that is essentially all the machinery, and that would be just, yeah. You don't want to, yeah, they don't want to use that because that's a hard theorem. So the idea, so Lawrence and Venkatesh give a separate proof. Well, they don't prove that all these things are semi-simple, but they at least prove that there are only finitely many exceptions. So they prove that there are only finitely many points here that do not give rise to semi-simple things. So all right, so. No, I don't think it does. I don't think it proves the semi-simplicity.
So it literally proves Martel conjecture, but not the trade plus and semi-simplicity.
I think that's right. Yes. Okay. So. Okay. So let's see. So I want to put this in a more usable form. I mean, if you want to use this, you have to be able to compute both of these numbers through both of these dimensions, and it'll be. Let me describe something you can do to work on the right hand side here. To something how you can understand this dimension a little better. So let me take the complex points. Yeah, so first of all, I explained, I guess last time, that you could, if you want to, you can replace the p-adic period map by the complex period map, because the Zariski closure of the image is the same, because they're both given by power series with coefficients in the number field. And so if I'm working over the complex numbers, let this be the universal cover, in the sense of topology of y of c. And then what you can do is you can. Yeah, okay. Okay, yes, that was intended. Yeah. I'm not assuming that y of c is simply connected. Yes. So, all right. So then you can. Okay. So we have the period map that we talked about before, that went from some little analytic open disk in y of c to the flagged variety that was obtained by transporting all the different the filtrations on the different de Rham cohomologies horizontally to move them into one de Rham cohomology, and then this is classifying the filtrations on that one space. Yeah. So, but now you can analytically continue this so that you can't analytically continue it across the whole variety y of c, because if you go around in some loop, and you might come back to values, the values might not agree with what you started with. But on the universal cover, there's no problem. So you can analytically continue this to get a complex analytic map. I'll call it period tilde, which is defined on the entire universal cover, and that goes to here. And and you can fit this into a diagram. So let's take this universal cover and this analytically continued map. And I can restrict to the points here that map down to the base point, y0. And so that's going to be one fiber of the universal cover mapping down to y of c itself. And that fiber is in bijection with the fundamental group. Namely, if you have an element of the fundamental group, you know that's a loop in the base. But you can use that, you can lift it to a path in the universal cover, and you see where it ends. And that'll give you some other point above the same base point. And so, okay, so I'll view this as a subset here. And if you restrict, and now there's also from here, there's the monodromy representation that sends this into GLV. And so what is this? If you have a loop in Y, you take the base point, you look at the cohomology, say Betty or Durham, whatever you want, of that base point, and now you follow the cohomology as you go around the loop. And you have a way to, as we said, locally we have a way to identify nearby fibers using the Gauss-Manin connection, or else using the Betty cohomology. You just follow the Betty cohomology around. But then when you come back to Y0 again at the end of the loop, well, you'll come back to the same vector space V, but your basis will have changed to a new basis, and therefore you get an element of GLV that measures the change. So that's the monodromy representation. So every loop gives rise to an element here. And there's a way to fill this in. I can put something here, which is just sending G to G applied to the starting filtration of the starting Hodge filtration on V. Because the way that this period map is defined is it's also defined by looking at how the filtration on the Durham cohomology changes as you go around the loop. So, all right. Okay, so this is a homomorphism, this top row, and let me also define here what's the monodromy group, which is sort of the image, except let me take the Zariski closure of the image here and call it gamma. So that's what I'm going to call the monodromy group. So so this is the Zariski closure of the image of this representation. And so this is a homomorphism, so this is going to be some algebraic group inside GLV. Okay, so I can talk about its dimension, for example. And so the point of doing this is that this gives me a source of things that I know are going to be in the image of the period map. Because if I start here, if I go this way, I see that I'm getting points in the image of the period map. But I can also go this way, and that shows that gamma applied to fill this filtration, all of that is going to be in the image of the period map. So I can, so this will let me prove that this period map has large image. Okay, so what's the upshot of this? Okay, so the conclusion of this is that of this little discussion, this little board here, is that, well, the image of the p-adic period map, which is the one that appeared in this last corollary, Zariski closure, that's the same as the image for the complex period map on this little analytic disk or whatever it is. But because that's going to be the same as if I take the bigger period map, the one that's analytically continued, just because, if holomorphic functions satisfy an algebraic relation on some open subset, it persists to anything, just because, if some holomorphic function is 0 on some tiny disk, it's going to be 0 on the whole space. So yeah, so this is all there. And now the point of this is now this is going to contain, it's going to contain the image of the monodromy acting on sort of this point. This is one point of the flag variety, and now you move it around by the monodromy group, which is acting on here, and then we know that that is all going to be contained in the image of the period map. So, okay, and then I guess I could take Zariski closure just in case it's not already closed. All right, so
Can you explain the first equality again? I know that the coefficients would say it, but they're in 3
this one.
Take a Zariski closure of the image of y of O v. Is there?
So you're talking about this equality? Yeah. So, right. So this is because the period map comes from the Gauss-Manin connection. So both of these maps are expressed in terms of solutions to differential equations, and those differential equations are algebraic over k. So they're algebraic. They're differential equations where the coefficients are functions, algebraic functions with coefficients in k. So the solution is given by whether you're doing it p-adically or complex analytically. The solutions are given by evaluating power series, and the power series are the same. They're power series that are just formally, you can define, there's the formal solutions to differential equations.
I was concerned about y of O v versus y of k v or something.
So the period map, I mean, I've restricted the case where I just have one residue disk.
Yeah.
And so we're just looking at one residue disk. So and we're looking in the neighborhood of 1 point in that residue disk. And so, I mean, you could restrict to any small analytic neighborhood of that point, and you'd get the same Zariski closure, because it just the power series converge on the whole residue disk.
We have explicit direction y. This isn't for some general y or something. That's fine.
Yeah, it's for this particular curve. Yeah, okay. Yeah, I mean, in general, this p-adic, this thing would be defined only on one residue disk inside YOOV. But here, I've in the big diagram, just to simplify the diagram, I mean, yeah, okay. All right, any other questions? Okay, so let's take a break then, and then I'll finish by doing an example of how you apply this to actually prove fineness of something. Except I'll prove the fineness of solutions to the S-unit equation. All right. Yeah. So I guess maybe what I could say here is that what we succeed in doing is we can replace this by putting this gamma applied to this fill dot Zariski to make it easier to compute what's going on the right-hand side. That was the point of this discussion. Okay. Anybody? Last chance before I erase the big diagram.
Just one last question. So the equalities between images, not dimensions of images, right? So for the image of the period of tilde, when it is very closure, it's the same. But the images of period of tilde without taking the rest of closure are not necessarily the same.
Well, I mean, they don't even exist in the same space because one is a set of complex points, and one of the. I mean, you mean this and this?
I'm talking about the second and the third.
Oh, this one.
Yeah.
Well, this one could be larger, but it's just sort of the analytic manifold that's sort of extending the. I mean, because this one is sort of this one restricted to a small disk. It's like this. This is some this is some sort of immersed complex manifold, and this is the same thing except restricted to a small disk. So Zariski closure is going to be the same.
But before they were
Yeah, this is just like a little open subset, in this. Except, I mean, it's not. I mean, it's immersed, so it's not. I mean, this could be winding around, so it's not necessarily, literally a submanifold. But yeah. Okay. All right. Last chance before I erase the big diagram. Okay, so we're officially in break right now. Okay, so now what we're going to do is we're going to actually try to apply this into a particular instance of bounding integral points on curves. I mean, the method. I mean, in Lawrence and Venkatesh, they explain how to do it for all instances. I mean, I mean, they prove reprove Faltings theorem for any curve over a number field. For lack of time, we're just going to do this. And we're going to, okay, so, and this variety, this is over some ring of S integers. I mean, you can also think of this as the equation, as the subvariety t plus u equals 1 inside, well, okay, so it's a set of solutions of t plus u equals 1 inside gm cross gm. I mean, because if you say that t is not 0 and u is not 0, and then if you think about what the possibilities for t are, then the possibilities for t are exactly that. So this, yeah, this is via projection to the first coordinate. Yeah. So that means that if you want to know what the S integral points are, then these are just going to be the S units, such that 1 minus it is also an S unit. Okay. So and as usual, the goal is to prove that this set is finite. Okay. So all right. So let's try to do this. So in order to get started with the Lawrence and Venkatesh method, we need to choose a family of varieties over y. So we have to choose the x over y. And so I'm going to try to do this. Well, I mean, I'm going to first do something that doesn't work, but we'll fix it later. So let's take the family. Let's take the Legendre family of elliptic curves. So that means that for each t, each point t, each number t in here, each of these numbers, then we take the elliptic curve that's given by the equation y squared equals x minus 1, x minus t. So I'll call that E sub t. Yeah, of course, as usual with elliptic curves, I really mean you take the projective closure. Yeah, so it's a nice model of. Yeah. Okay. Okay. Well, that's a nice family of elliptic curves. It makes sense for all t that are not 0, 1, or infinity, and so that's a smooth, proper family. And well, of course, the only interesting cohomology for elliptic curves is the first cohomology. So I is going to equal 1. And then the first cohomology is a two-dimensional thing. So dimension v is 2. Okay, so now we have to compute. Okay, so now let's look at this inequality. We hope that this inequality is going to be satisfied. But let's see what actually happens. So what is the left-hand side in this inequality? What's this dimension of this centralizer? So that's the dimension of this algebraic subgroup. The things that commute with this Frobenius operator. And this Frobenius operator is the thing, I mean, it's this thing whose, its eigenvalues are these numbers of square root of q. But the problem is that this thing could be, the dimension of this could be as large as 4. I mean, for example, so e.g., if we're in a situation where this Frobenius were like multiplication by minus p, which can happen for a supersingular elliptic curve over fp squared, it could be something like that. So so it could be like this for supersingular. If you're in a residue disk that had supersingular reduction over fp squared, say, then you would be in trouble. Well, at least that's large. And how big is the right-hand side? Well, you'll see very soon this is not good. Because what's the flag variety in this case? I mean, this is describing the possible Hodge filtrations on this two-dimensional de Rham cohomology. But the Hodge filtration in this case just consists of just giving a one-dimensional space inside here. So this is just, the flag variety is just there's only one intermediate vector space in this flag. So it's like it's just the parameter, it's just parameterizing one-dimensional subspaces of a two-dimensional space. And so, that's not very big. I mean, that's just like a copy. As a variety, it just looks like P1. And so actually, it doesn't even matter what these things are. I mean, the Zariski closure is not going to be bigger than the whole variety. So, right. So, I guess I could say what it is. I mean, the gamma is. I mean, I could tell you what gamma is, but it's going to be gamma is going to be. It's the monodromy group for this family. It's going to be, well. It's okay. The image of the monodromy is going to be some subgroup of. It's going to be like some congruent subgroup in SL2Z. It's the one that corresponds to the Legendre family. So it's. So gamma is going to be the Zariski closure of some finite index in SL2Z, finite index subgroup of SL2Z. But I mean, it doesn't matter because so it's going to be something, yeah. But that means that if I take this and apply it to my theorem, well, it's going to be as big as it could be because this SL2Z is going to move this any one-dimensional subspace all around, and the Zariski closure of that is going to be the whole space. But anyway, it's one-dimensional. So, and as you know, 4 is not less than 1. So 4 is less than 1? No. So this is a fail. Okay. All right. So this didn't work. So I'm going to have to modify I'm going to have to choose a different family in order to make this work. Okay, so let me start over. And, okay, so now this is going to be attempt number 2. And actually, there's not going to be an attempt number 3 because attempt 2 is going to work. So this is the good one. Okay, so the plan is going to be to do this. So y is still p1 minus 3 minus 0, 1 infinity. But I'm going to start by choosing finite étoile cover y prime. That's given by the mth power map for some m. So t is the coordinate here, and z is the coordinate here, and this is the mth power map. So this is also, it's like p1 goes to p1 via the mth power map, but now I remove the mth roots of all these things. So I remove 0, and I also remove all mth roots of unity and infinity. Okay? So I get another curve that has more punctures. And then on top of this one, I'll put, the Legendre family. So above each z, I'll have the elliptic curve E sub z that's given by y squared equals x minus 1, x minus z. Okay, so, all right, so that's going to be my family. Now, it's a little bit weird in that if I take the fiber of this, so I'm going to apply it to this total map from x to y. And it's a little bit weird in that if I take the fiber above t and look at it geometrically, say over k bar, then what does that look like? Well, if I take the fiber here, I'm already going to get m different points. And then above each of those points, I get an elliptic curve. So geometrically, this looks like a disjoint union of m different elliptic curves. So of the elliptic curve, where I take the elliptic curves corresponding to all the different mth roots of t. And yeah, so I'll just write like this. So okay, so in particular, note that this is, these fibers are geometrically disconnected. But that's okay. I mean, nobody said x had to have connected, geometrically connected fibers or anything. It just had to be smooth and proper, which it is. So that's okay. All right. So actually, let me. Okay. So that's what I'm going to do. I mean, I should tell you what m is going to be. So for that, I'm going to have to this positive integer m. And for this, I'm going to take all the 2 power roots of unity in the number field. So I mean, that's going to be some. I mean, you know that the roots of unity are a finite group. So this is the 2 CELO subgroup of that group. This is also a finite group. In fact, it's also cyclic, as you know. So it's generated by 1 root of unity, and m I'm just going to be defined to be the order of that root of unity. So which is going to be some power of 2. So yeah, this is a power of 2. A power of 2. All right. So and let me enlarge By the way, when I'm proving fineness statement like this, I'm always free to enlarge the number field and then enlarge S if I want to, because that'll just make the set bigger, the set of integral points. So let's enlarge K, the number field, and the set S. And by doing that, for example, I can throw in all the 8th roots of unity into K. All right? And guess what? If I do that, then M is now going to be at least 8, so which I'm going to need later in order to make my inequalities work. So, all right, so do this, and let's enlarge S as well so that it contains anything that could possibly be bad for this situation. So I'll make it include, well, all the places above 2, all the places above infinity, all the places that are ramified in K over Q, so rank. And then also all the places that are above, well, this looks kind of self-referential, but places above, places below S. So what I mean is, if S contains one of the places above 7, it should contain all the places above 7. Okay? So, all right. So you can just assume all that. All right. All right. So I'm gonna. Okay. There's gonna be some tricky reduction that I'm gonna do first before actually getting into the dimension calculations, and because it won't quite work everywhere, but in all the residues, so I want to make some simplifications. So let me first try to look at the set of solutions where the t is not a square. Or sorry, yeah, not a square. Let's call that u. So the first thing I want to prove is that if I take all the solutions to the S unit equation, then they're the non-squares, they're the squares of the non-squares, and then there's the 4th powers of the non-squares. I mean, you can imagine, if I went on forever, this would be kind of obvious, because you start with something that's, if it's not a square, you take a square root. And if that's not a square, or if it is a square, you take a square root. And if that's a square, take another square root. And you keep going until you find something that's not until it's not a square root. But I'm claiming that actually you don't have to go forever. It's enough just to go to m. To that, whatever that power of 2 that is. And so that's okay, this is just some elementary algebraic number theory. So the first thing to argue is that if you start with one of these solutions to the S unit equation, so both of these are S units, and if it is a square, so if the t is a square in K, then the square root of t and 1 minus, then square root of t is going to be another solution to the S unit equation. And, well, this is kind of obvious because, well, I guess the first part is really obvious. If t is a unit, then so is square root of t. And as for the second one, well, I mean, 1 minus square root of t is a factor of 1 minus. Yeah, you have this equation in the algebraic integer. So if that one's a unit, then both of those have to be units too. All right. So yeah, that's okay. So all right. So now let's prove this. So start with a point in a solution here, and well, so there are two cases. Either if it has an mth root in the field, sorry, if it does not have an mth root, then what you do is you just keep taking square roots of t until you get stuck. And this tells you will get stuck before you get to the end, before you get to the mth root. And therefore, t will be inside u union u squared union up to, well, you get stuck before taking an mth root, so you'll be in here. Okay, but what if t does have an mth, if t is an mth power? So I'm claiming that it's actually, okay, so we know that t is an mth power of something, but it's not clear that that's going to work because this mth root might also be a square. And U is supposed to be only consisting of only the non-squares. So what do you do if T is the mth power of something that is a square? Well, it's also the square root of this other thing. And this one, well, they can't both be squares. Because this, if you take this number and this number, these are not, so one of these is going to be a non-square, is in U. Because, I mean, if they were both squares, then zeta would have to be a square. But zeta was the generator for the two power roots of unity. So it doesn't, yeah. OK. OK, so that's the end of the, so that finishes the proof of this lemma. And so as a consequence of this, therefore, it suffices to consider the solutions that are non-squares. So that it suffices to prove that this set U is finite. Because then this union shows that the entire set of solutions is finite. OK, so that's the first reduction. Another thing you could say is by Hermite's finiteness theorem, there are only finitely many possibilities for this field K where you join the mth root of T, when T is ranging over the elements of U. Because all those extensions, I mean, if you're taking the mth root of a unit, it's going to be unramified away from M and away from, and away from the bad places. But yes, yeah.
If you had a p squared affinity for some odd prime t, put this p instead of 2, right?
You mean if for
If you had a p squared affinity in the 3, you could
for this kind of argument? I guess so. Yeah. Yeah. I hadn't really thought about why they used 2, but anyway, I guess they just wanted 1 prime to.
You always have the second root affinity. You need the p squared affinity if you.
But you can always put in the p3. I mean, here I put in all the 8th root of unity. So, yeah. Okay. Okay. Anyway, I guess they just So, all right. So we have. So there. I mean, so these are extensions of bounded degree and of bounded ramification. They're unramified outside S and outside 2. And so they only find the main possibilities. So if I'm trying to prove finiteness theorem, I can just restrict to the solutions that give all. I can just fix one of these possible fields and look at the solutions that give rise to that field. So I might as well just assume. So therefore, I can just assume that this field is a fixed one. Is a fixed field. So let's call it L. Okay. So L. Here L is, what kind of field is it? It's a Z mod MZ. It's a cyclic extension. It's a Kummer extension of K. Because I mean I have the mth roots of unity and I just adjoined an mth root of something that was not a square. So it's a Z mod MZ extension, cyclic extension of K. Okay, so. All right, now let me choose a place V of K that's inert in this extension. I can do that because it's a cyclic extension. So some V whose Frobenius generates the Galois group. So some unramified V that generates the Galois group. And then, okay, so then I can let L sub V, I mean, there's a unique place of L that's above V, so I'll call that V also. And I can take the completion, do the completion. The L above V. So that's now going to be an extension of KV. In fact, it's going to be a cyclic extension of KV with the same Galois group because it's inert. So, and all these are unramified. Yeah, I guess V is also supposed to be outside S, away from all the bad primes. So maybe I should say that, outside S. So all these fields are unramified. LV and KV, and they're all unramified. And all right, and so now I have this vector space V from the general setup. That's in this context is going to be the first de Rham cohomology of the fiber. So above, well, okay, so I mean, I'm assuming I have some y0. Otherwise, otherwise there's nothing to do. So I take that and I base change to this kv and take the l-adic. Oh wait, there's no qp here. Sorry, this is just the de Rham cohomology. Yeah. Okay. So what kind of thing is this? This is it's as a vector space over kv. I mean, so this is a bunch of elliptic curves. It's a disjoint union. Geometrically, it's a disjoint union of elliptic curves, and that means that its de Rham cohomology is just going to be the direct sum of the h1s of all the components. And so, in each elliptic curve has a two-dimensional h1. So this whole thing is going to be, and there are m elliptic curves in that disjoint union. So this whole thing is going to be a vector space of dimension 2m as a kv vector space. On the other hand, this thing also has the structure. If I didn't base change to k bar, I could also think of this as being one elliptic curve over the degree b, over this degree m extension. And if you view it that way, then you can take, this would be the same as the h1 for that elliptic curve over LV. And so you can also view this as a two-dimensional LV vector space. All right. So, okay. So let's see. So now I think I'm ready to start looking at the. Yeah.
Would you be matching them up with any of the reductions in the general case, or this is just?
No, this is just some ad hoc thing that they did for the S-unit equation to simplify things. I mean, it simplifies things, and it's going to simplify the computation of these dimensions and make sure that the dimensions are what satisfy the inequality. Yeah, it seems kind of what?
I thought they had to take some large, maybe it was a highly ramified extension. I thought they had to take some large extension in the general or general.
You mean if they're proving Faltings theorem instead of the S-unit equation? Yeah, they have to do something similar. They have to do some other ad hoc thing to pass to a situation where these inequalities hold. So there's, in all the, okay. Anyway, so. All right, so let's now, okay, so let me now, so now we're in the setup where I want to compute these two dimensions. And hopefully this number will be less than that number. So, all right, so let's see. So let's work on the left-hand side first. So the left-hand side is this dimension of this centralizer, yeah? So we need to compute the dimension as a KV algebraic group of the automorphisms that commute with this power of the crystalline Frobenius. So the dimension of that. So where this V, I'm thinking, I guess, okay, so maybe I should say this V I'm thinking of as a KV vector space here. But there's a little lemma you can prove, some little linear algebra thing, where you can prove that this is actually the same as if you considered the automorphisms of V as an LV vector space, but then raise this to the mth power to make it LV linear. Okay, so there's some sort of semi-linear, some little lemma of semi-linear algebra that I think I'm going to skip because we don't have much time. But you can, this is just some, it doesn't have anything to do with de Rham cohomology or elliptic curves. It's just something about, some silly little. No, you don't have to multiply by anything. Yeah, it's just equals. Yeah. Okay, so anyway, let me just accept. Yeah, if you want to know the reference, it's lemma 2.1. All right, so this is lemma 2.1 in the Lawrence Venkatesh paper. Okay. So I mean, basically, you can reduce the case. I I mean, it holds for any cyclic tall algebra. So you can base change to an algebraic closure if you want to, and then the Gauss automorphism is just sort of rotating the coordinate. I mean, then your LV is like a product of copies of the algebraic closed field. And anyway, it's not too hard. So yeah, but now this already gives you an upper bound on this thing, because now this is only a two-dimensional vector space. So this is now a subgroup of GL2 of LV. So this is going to be at most. So this is at most 4. So which is it's a nice small number. All right, so that's a nice, what?
The same 4 as before.
Yeah, but we can hope that maybe the right-hand side will be bigger than 1, so, or even bigger than 4. So, all right, so, yeah, so let's see. So now we have to compute the right-hand side, which means we need to compute the monodromy of this, the monodromy group for this family. All right, so this is the right-hand side, and so this is okay. So if you're following the paper, this would be lemma 4.3. Okay, so maybe I'm not going to. Let's see. Yeah, not too much time. Okay, so anyway, what happens is that gamma, the monodromy group. Yeah, so I mean now you really just you're doing a little complex analysis. You're like drawing little loops around the base, and you're seeing how they act on the cohomology of the fibers of this disjoint unilimited curves. If you go around a little loop around 0, then it's like going around a little loop. Well, okay. Anyway, so it's some little calculation. That's not too hard in this case. And if you try all the different loops here, actually they're not too many. They're just like a loop around 0, a loop around 1, and yeah. Because the fundamental group here is just free group on 2 generators. So you just figure out you can just calculate what those generators map to, and you conclude that this monodromy group contains a finite index subgroup of the product of the SL2Zs of all the different elliptic curves. So the things above this. So T0 is my initial point down here. The ones. Oh, I guess I called it Y0 here. Whatever. Okay, Y0 is T0. As a number, the point Y0 it corresponds to the number T0. Yeah. So you have this, and this is inside. It's a Zariski. I mean, this is happening inside the general linear group of this space of the H1s of the fibers. So I mean, you could take whatever kind of complex cohomology you want. So it's a Zariski closure. Gamma is going to be the Zariski closure of something that contains this in here. But that already tells you that gamma is going to be at least as large as the product of all the SL2s in there. So and so now if you act by this on the Hodge filtration, yeah, and what does this look like? What does the Hodge filtration for a fiber of this look like inside this vector space? Well, it's going to be like a direct sum of a one-dimensional space in each component, but now you can move those one-dimensional spaces independently according to this lemma over because you have the gamma is going to contain the SL2 in each component. It's going to be like the gamma is going to contain the product of all the SL2s, and so using those, you can move that filtration to any other tuple of one-dimensional subspaces in here. And so that means that this Zariski closure is going to actually be, the product of all the different P1s. The P1s, each P1 is classifying the one-dimensional subspace of one of these factors, and so it's going to be. So you can move around the Hodge filtration as much as you could possibly imagine. So it's going to be at least. Of course, you can't move it. You can't move all of them until. Well, you can't make it You have to, it has to preserve, it has to act within each piece. But other than that, you can do whatever you want. Yeah, but that's already good enough because this tells you that the dimension of this image of this action, this already gives you, I mean, this tells you, in fact, this computes exactly what the dimension is. It's 1 plus 1 plus 1 plus 1, m times. And well, and guess what? M is at least 8. So and I guess the point is that, yeah, that's 8 is bigger than 4. So the conclusion, okay, so what's the conclusion from all this? From these calculations, from the left-hand side and right-hand side? We've proved that the semi-simple points, the points whose Gauss representation is semi-simple, is finite. Okay, so we're not quite done, because now we have to worry about, well, could there be infinitely many points that have a non-semi-simple representation? And so for that, okay, so this is the argument that's in general is quite hard to handle, but there's a, well, if you let me use some sledgehammer, I can solve this problem. So I'm going to use the sledgehammer I'm going to use is Serre's open image theorem for the image of Galois on the tape modules of elliptic curves. And that, I mean, I shouldn't have to use that. I mean, because it's kind of bad to use that because using this is not going to generalize very easily I won't be able to use this trick for the proof of the Mordell conjecture because we don't know that, it's not quite, yeah, it's not true, anyway. Yeah, so this is sort of overkill, using this, but what am I going to do? I've got 5 minutes left. So, to be fair, Lawrence and Venkatesh do give an alternative way to do this without using something as hard as Serre's open image theorem. They give it's hard in a different sense. They use more p-adic Hodge theory but anyway, yeah, and Hodge-Tate weights and stuff like this. But what they do is it's easier to generalize. That's the point of what, if you use this other method using Hodge-Tate weights and so on, it's easier to generalize. So, okay, but I'm just going to take the easy way out and use Serre's open image theorem. So by Serre's open image theorem. This tells me something about the Galois representations associated to elliptic curves. Yeah. It tells me that if I take one of these elliptic curves, that's the components of one. It's in the fibers. If it's a non-CM elliptic curve, no complex multiplication, for all the z, okay, so let me say given t in y o, if EZ is non-CM for all the mth roots with z the m equals t, well then I know how the Galois group acts on the cohomology. It's going to act by some finite index thing in the GL2 ZL of each fiber. And I know, and semi-simple doesn't change if you pass to a finite index subgroup. So in this context, I will know that this Galois representation is semi-simple. Because I know everything I know what the, if you pass then to a finite index subgroup, maybe to this field L, then I know what the image of Galois is. It's going to be a subgroup of the products of all the GL2 ZLs, and that means that the simple components are just going to be these two-dimensional pieces, one for each elliptic curve, and which are irreducible representations because the group is acting by each of those two-dimensional pieces is irreducible, and so that means that this is semi-simple. Yeah, and so, all right, so if you have a T such that all of these curves are non-CM, then it's okay. And then how many of these could be non-CM? Well, I mean, these exist in just a number of fields of bounded degree, and there are only finitely many CMJ invariants in fields of bounded degree. So there are only finitely many bad numbers Z. I mean, of this degree, even in Q bar, and so. And each of the, I mean, you take the m-thirds of all of them, and so there are only going to be finitely many bad T's. So this argument that I just gave, it applies to all but finitely many T in here. So okay, so that's the end, because that shows that for all but finitely, I didn't prove that all of these representations are semi-simple, but there are only finitely many ones that are not semi-simple. And then, yes, that handles the non-semi-simple ones, and this, right, this is gone, wait. And this handled the semi-simple ones. Okay, so that finishes the proof of the fineness of the S-unit equation. And then, well, then you can do something similar for the Mordell conjecture, except everything's much harder. But it's the same kind of ideas, it just sort of, you have to do, I mean, what's especially harder, well, I guess, so what are the two really hard things are, first of all, you have to do these monodromy calculations. But now it's going to be a much more complicated family. It's not just going to be a disjoint union of elliptic curves. It's going to be some more complicated thing. Again, it's going to be some finite thing, and then there's going to be some family of curves above it. But they're going to be higher genus curves and everything. And then you have to really do a lot of topology. You're like writing down little pictures with little loops in them and stuff like that over the complex numbers to compute this. And the other hard part is also this, is again to eliminate these, to handle the non-semi-simple case, and to have some a priori way of proving that there are only finitely many non-semi-simple ones. Okay, so anyway, so that's the end of this course. So thank you all for coming.